Hey guys, welcome to another video here on our new unit for the semester, which is covering radicals, graphs of them, how to transform them, and how we can today find key features of these graphs and functions, specifically for square roots and cube roots. So when I'm thinking about key features, these are the ones I want you to be able to know. So some of these you've seen before, whether in past years or even last semester. Domain and range, probably from previous years. We have talked about x-intercepts, y-intercepts, and the idea of a graph that increases or decreases over time. Absolute max and min. These are the summary of all the key features that we can find when we graph a radical function. So briefly, what do these mean? Domain, think about where does a graph exist? From left to right side of a page. Are there places where the graph doesn't show up? Or are there places where it does? You're thinking about x values, reading from left to right, where does the graph show up? For range, instead you're thinking about y values. Think about the y-axis, which is up and down. Where does the graph exist? List that as a range, as an interval from down to up. Another key feature that we'll talk about is absolute max and min. So this would be where you might have a highest coordinate point, which would be an absolute max, versus a graph's lowest coordinate point, which would be an absolute min. X and y intercepts, just does the graph ever cross the x-axis, does it ever cross the y-axis, and then the idea of increasing or decreasing over time, either towards the right side of graph or to the left side. So these are some key features that we'll need to be able to identify. And for cube roots, we're not going to focus as much on those because if you can look at a cube root graph, a lot of what we see here won't apply very differently. For example, domain and range is always the same, right? Take a look at this cube root graph up here. It doesn't matter if it moves right or left or up or down or stretch or shrink or even reflect. None of that matters because the range and the domain are always all real numbers. The graph goes everywhere off to the left and to the right forever. Doesn't matter if you move it, stretch it, reflect it. Okay, always goes left and right forever. The range is also all real numbers because it increases one way and decreases the other. That's always going to happen for a cube root graph. It'll increase one direction, decrease the other. Therefore, it will never have an absolute max or min. Think about this. Okay, that's pretty high. But I could always increase or find a higher coordinate point and keep finding a higher one. There's never an absolute max and there's never an absolute min. The graph decreases forever, one direction as well. There is no lowest point. And there will always be an x and y intercept here. That's because the graph, again, will forever go up and down. So at some point it has to cross the x-axis and the y-axis. So for cube roots, we're not going to focus on that too much. It doesn't help us to identify these key features in context as well as a square root example might. So that's what we're going to do here. And we're going to go over graphing one more time, which we did in our last video as well. So I'll actually start there. Our parent function in this case is clearly a square root graph, right? We have a jump, something that looks like it has a starting point and then jumps somewhere. In this case, it jumps up towards the right, just like the parent does. But the starting point of that jump is different, right? In this case, you went left by 1, up by 1. Left 1 unit, up 1 unit. There's no reflection. Okay, so these are the only two changes that you have, the only two transformations. H and K have changed for this parent. Okay, remember your transformations, A, B, H, and K. And therefore, because it's moved left 1 and up 1, our transformed function, which should have a different name, will equal still a square root. You'll still have x as well. Left 1 changes h. Okay. By adding or subtracting next to x. In this case, we're going to add inside of our parent, inside of our function. And then up by 1 changes k. That's a number to the outside of our function that changes. In this case, that's also up by 1, okay, but for a different reason. So up 1, outside, left 1, inside, add by 1 in both cases. Okay, so that's what we did last class. Now we're going to look for key features of this graph. So, for example, the domain. Does the graph exist anywhere over here? And hopefully you can see that it does not. Okay. The graph exists starting at this point. Now, remember, domain, we said earlier, means that we're reading the graph from left to right along the x-axis. So, where's the first point where the graph begins to exist? And hopefully you see there, it starts to exist when x equals -1. And where does the graph stop existing, or does it ever stop? Well, if you look towards the right, no, it does not. It keeps going. The graph exists all the way towards the right from that starting point of -1. Okay. Off towards positive infinity, towards positive numbers. The graph exists when x equals +1, when x equals +4. There's a graph. Okay. It keeps going towards the right forever. So the graph includes -1, that's why we use a little bracket here. Okay. The domain, the graph, you can plug in -1 here and you will not get an error back. But if you try to plug in anything less than that, if you try to plug in -2, for example, okay, the solution will be imaginary. We're not dealing with imaginary numbers in this unit. They don't show up on a real number graph. So, -1 is the first number that shows up. That's bracketed. Any number after that can show up all the way towards positive numbers, towards positive infinity. That's where the arrow is pointing towards the right. Range, in this case, okay, we're looking for y values, down to up. Where does the graph exist? Okay, the graph does not exist anywhere down here. The first place that the graph starts existing for the y coordinate is at +1. So include that, bracket it, and the graph keeps going up forever. So in this case, it's also heading towards positive infinity, but for a different reason. Again, range, look from down to up. Where does the graph show up? Domain, look from left to right. Where does the graph show up? Make sure you bracket your numbers if they're included. And infinity, you can never reach infinities, so you're always heading towards that direction. Put a parentheses around those. All right. Now we can move on and talk about other key features like absolute max or min. Like we said, sometimes that doesn't happen, but that's only for cube root graphs. In this case, we do have either a max or a min. So think about, do we have a highest coordinate point? Do we have a lowest? Hopefully in this case, you see that we have a lowest. Okay. The lowest coordinate point here is the starting point. It's the jump, right? Okay. And it is the lowest because this has not been flipped upside down. It's not reflected. Okay. It doesn't look something like this. This would be an example of an absolute maximum. Here we have an example of an absolute minimum at coordinate point -1, 1. So x equals -1, y equals +1, x, y. Okay, that's where we have an absolute minimum. So lowest point there. X-intercept. Does the graph ever cross the x-axis? No. There is no x-intercept in this case because the graph does not cross the x-axis. Now it does cross the y-axis, right? At 0, 2. You can confirm that if you wanted to by taking a look over here. If you plug 0 into x, what do you get back for y? 0 plus 1 is 1. The square root of 1 is 1, and 1 plus 1 is 2. So the function should match your graph in terms of coordinate points. And does the graph increase or decrease as we head towards positive numbers along the x-axis? In this case, it increases. As you can see, the graph goes up over time, not down. This would be an example of a graph decreasing towards positive infinity. So keep that in mind. So those are our basic key features that we'll need to keep in mind for when we're looking at something like a graph. But I do have one more example I want to go over dealing with a real-world problem. Okay, so this is where we'll end off for today. This mainly discusses domain, and it could discuss range as well. In fact, it does. And this scenario involves a bus that carries people, right? And this bus has a certain miles per gallon, MPG, miles per gallon, that it gets as it's driving. The more people that you see on this bus, the more the weight will cause the bus to have less miles per gallon. So how do we model that? Apparently by this function. Okay. So what I would want you to do is think about that real world scenario. You have a bus, carries people, okay, gets miles per gallon. That miles per gallon gets worse over time if you have more people. Please try to answer these 3 questions. Number 1, what does the number 25 mean in the context of this function? Number 2, what is the domain here? Okay, what number can we plug into x? And number 3, what is the graph then going to look like in general? Okay, so number 1, what does 25 mean? Well, if we want to just look at the 25, we have to somehow get rid of this negative cube root of x. Okay, that has to be a 0. So, in other words, when there's 0 people, okay, let's pretend you had no passengers, then the bus could go 25 miles per gallon. If no passengers, if x equals 0, then the bus goes 25 miles per gallon. Okay. The domain, in this case, is what values can you plug in for x? Okay, think about what numbers would make sense in this real-world scenario. Now, remember, for normal cube root graphs, the domain, the range are always the same. Domain usually negative to positive infinity. The range also negative to positive infinity. But for this real-world scenario, that doesn't happen here. Because can people be negative numbers? Can you have a negative amount of people? Can you have a decimal amount of people? No. It has to be whole numbers in this real-world context. Now, there might be some examples in other scenarios, like with money. Then you can have decimals. Can't be negative, but you can still have decimals. Or credit cards, right? You can have negative credit card balance and decimals. So it just depends on the scenario here, but since we're talking about people, okay, you can have 1 person, 2 person, 0 persons, 1,000 persons. Whole numbers is what we're looking at. 0, 1, 2, 3, 4, etc. Okay, all the way off towards infinity, but they got to be whole numbers. And so, what does the graph look like? Is it going to look something like this? No. Think about this, right? This graph has decimals, right? If we look at 1.5 comma something, there's a graph there. But down here there shouldn't be because we can't have decimals. X cannot be a decimal. X cannot be a negative. So the graph might look something like, I don't know, I'll make something up. Something like this. So up here, when x is 0, y is 25, right? 0, comma 25. We already discussed why that is. If you plug 0 into x, you get 25 back for y. If we plug 1 into x, okay, because we can do 1, that's a whole number, that's fine. We'll get 1 comma 24. You can double check this for yourself. If you plug 1 in for x, calculate what is f of x when that happens. The cube root of 1 is 1. Negative 1 plus 25 is 24. So if there's 1 passenger, the bus gets 24 miles per gallon. Let's try a bigger number, like 8. Okay? What happens if we had 8 passengers? That'd be way over here. If we had 8 passengers, the cube root of 8 would be 2. Negative 2 plus 25 would be 23 miles per gallon. So that would be something like, when x is 8, y will be 23. That's another coordinate point. Notice, we're not connecting these dots though, because you cannot have decimals of people. So you could have decimals of miles per gallon, that's fine, right? If I plug in a 4 here, I can have 4 people. I will get a decimal number for my miles per gallon, that's okay. But you can't have decimals for people. So you could have dots in between here. You could have a few more dots at, 2 people, 3 people, 4 people, etc. Okay, 8 people. But the graph is going to look like dots. It's not going to look like an actual fully connected graph because the domain is restricted to nothing but whole numbers. Okay, so that is our video on key features. We have one more video for this unit that we'll talk about next time on solving radical equations. And that will wrap it up, and you'll be ready for the next unit.